Okay, good morning. Unless there's questions, I'll just dive right in. So last time we finished talking about vector bundles, and I'll have a bit more to say today about vector bundles. And we started talking about a special example of a vector bundle, namely the tangent bundle. We haven't yet seen that the tangent bundle is a vector bundle, but we'll do that today. But what I finished the lecture with last time and spent a bit of time sort of working this out was this relationship between tangent vectors. And so remember, our definition of tangent vectors was that a tangent vector was an equivalence class of curves where two curves are equivalent when they have the same derivative as they pass through x naught in a chart. Okay, and then we showed that that was independent of chart. Okay, then we had this non-chart concept, which is that of a derivation. And remember, the derivation is a mapping. So we'll see down here that it's a mapping from the set of functions of class CR into the scalar field, and it has some property, and you'll remember that property. So it was linear with respect to the vector space structure on here and here. And then it had this product rule structure, like so. Okay. So that's what a derivation was. So what we showed was that first of all, this thing is a vector space in a natural way, and then what we spent the remainder of the time, the last part of our lecture, on Monday, doing was understanding the relationship between the tangent space and this space of derivations. So we did this by first assigning to a curve. So remember, tangent vectors are, of course, equivalence classes of curves, and so curves play an important role in talking about tangent vectors. And so corresponding to a curve that passed through x naught at time 0, we defined this mapping, theta sub gamma, like so. All right. And then we proved that this thing was a derivation, right? So this gives us a way of taking curves, gamma, which pass through x naught at time 0, and assigning to those a derivation, right? So we proved that. So then we had this mapping which sent tangent vectors, so elements of the tangent space, which we denote by this. Okay, so it sent a tangent vector, which was an equivalence class of curves, to the derivation that we had defined up here, theta gamma. Okay, and so we proved some things about this. So we basically proved that it was linear. We sort of did that. What we really proved was that if you choose a chart and then represent the tangent space in the chart, we proved that the mapping v phi into a set of derivations, that thing was linear. But part of what we did there was we showed that there's a bijection between v phi and the tangent space. And so essentially what we did was we mapped the tangent space injectively, okay, into the space of derivations, right? And the vector space structure on here induces a vector space structure on here because it agreed with the vector space structure that you get on the tangent space from any chart. Okay, so in this way we kind of we proved one of the consequences of what we did last time was we proved the meaning of linear here. So we showed that this thing had a natural vector space structure. Okay. All right. So what I want to do at the beginning of the lecture today is say some things about this correspondence between tangent vectors and derivations. And I'm going to sort of broaden the things I talk about, and I'm going to just talk about a few things, and I will talk about them in yellow because these are important, things that are not um, central to the course. In other words, I'm not going to expect you to know anything about them on homework, but I think, and I'm not going to say anything in detail about them, but they're very important. Okay, so let me sort of entitle this discussion as things that we'd like to be true, but may not be true. And so, so part of this discussion is going to be about this mapping that we talked about last time. But like I said, I'm going to talk about some other things too. Okay. All right. So let me start by talking about things related to vector bundles. Okay. So we talked about various ways of combining or taking existing vector bundles and producing new ones, products, direct sums, pullbacks, subbundles, things of that nature. Um, and there were things there that I didn't talk about that you may want to talk about and are kind of natural to talk about. Okay, so if E um, pi E is a vector bundle, okay, we can consider the set of vector bundle mappings from E to the trivial bundle, Fm. So this is M cross F. Okay, so this is a vector bundle over M. This, of course, is a vector bundle over M with um, um, fiber being just the scalar field F, and the vector bundle projection here is just the projection onto the first vector. And here I'm considering these things as being defined over the same base. Okay. And so we can certainly do this. We have the set of vector bundle mappings from E into the trivial bundle. Okay, um, so if X is in M, okay, so let's suppose I have a vector bundle mapping here, and let me call it maybe lambda. Okay, then lambda of X. Let me write it as lambda sub X. So this is going to be lambda restricted to the fiber at X. So this is going to be just a linear mapping from E, the fiber, to the fiber of this thing at X, but of course that fiber is just the scalar field. Okay. All right, and if it's a CR vector bundle mapping, so I'm not being super careful here about regularity, so but it's at least continuous, then this mapping will be continuous. Okay, so and linear, okay, because part of the notion of a vector bundle mapping is that it's linear on the fibers, and so therefore this thing is in the dual. Okay, the continuous linear dual of E sub X. All right. Okay, fine. So you can certainly do that. Okay, so but what you can't necessarily do. What may not be the case is that there is a vector bundle. which captures this set of a vector bundle mapping. So there, what may not be the case is that there is a vector bundle. And what would you like this vector bundle to be denoted by? Well, you'd like to maybe denote it by E prime, okay? Because the fibers of this vector bundle are going to be the vector bundle mappings here on fibers, and those, as we just saw, are elements of the dual. So, maybe this object, you'd want it to be denoted by E prime, okay? So there may not be a vector bundle like this whose fibers are EX prime. And why is that? Well, this is corresponding to the fact that on um, the topological dual of a locally convex space, there is not a natural topology, and we need to have topologies for the fibers in order to make these things into a vector bundle in the sense that we've talked about, because a vector bundle is something that locally looks like an open subset across V, okay, and V is a locally convex space. Well, the V's for this vector bundle that we'd like to exist, the fibers are going to be these guys, and they don't necessarily have a natural locally convex structure. Okay. Okay. So when is this true? So this can be done. So let me emphasize. If um, uh, M, so if the fibers of E are modeled on Banach spaces. Or even just normed vector spaces in general. Okay, and the reason that this works for norm spaces is that for norm spaces, there's a natural topology for the dual. Okay. Namely the operator norm topology, which is locally convex. Okay. All right, so the dual bundle is problematic. Okay, so the dual bundle being the bundle of the duals. Okay. And so, for example, for those of you who already know a little bit of differential geometry, this means the cotangent bundles. We've been talking about tangent bundles, but cotangent bundles are problematic, generally speaking, in infinite dimensional geometry. Okay, if you don't know what those words mean, I'm just saying this for the tangent bundle. I'm saying this discussion right here applied to the tangent bundle. Okay, for the tangent bundle, this thing is called the cotangent bundle. Okay, good. So dual bundles don't necessarily exist in a natural way. So if we have two vector bundles over the same base, okay. All right, so again, this has to do with the lack of feasibility of what is sort of a natural structure in some settings. Okay. Okay. Um, there's generally not a vector bundle. And a vector bundle, and maybe let's call this thing that doesn't exist. Let me write it as E tensor F. Okay. Whose, and if you don't know what tensor means, don't worry about it. If you do, then you'll have some idea at least what I'm talking about. Whose fibers are the tensor products of the fibers. Okay. And the reason here is rather similar to the reason the dual bundles don't generally exist, and that is that tensor products don't necessarily have a nice topology. Okay, there's many topologies that you can put on the tensor product of two locally convex spaces. So let me maybe say it a little bit more generally for the tensor product of locally convex spaces. Okay, so maybe depending on how you want to do this, maybe there might be a natural among the possible topologies for the tensor product. Maybe there's one that you could work with, but the tensor product is, I'll just say it's problematic. So um, the tensor product. So when does it work of vector bundles? Does make sense. For manifolds, let me say it this way. It does make sense when the fibers of E and F are finite dimensional. Okay, so when E and F are finite dimensional, the fibers of E and F are finite dimensional, then the tensor product is again, the tensor product of E and F will again be finite dimensional, and so it has a natural topology. So all of the possibly many topologies that you have, locally convex topologies that you have for the tensor product, they're all the same in the finite dimensional case. Okay, and so in particular, I do mean to imply that even when the fibers of E and F are modeled on norm spaces, even Banach spaces, even Hilbert spaces, I do mean to imply that the tensor product does not generally make sense in that setting. Okay. All right. Okay, good. So those are two vector bundle constructions that don't make sense. Uh, Not, at least not naturally. Okay, good. So that's general vector bundle stuff, kind of left over from when we were talking about vector bundles. Now let me talk about some things related to this mapping here, which you may like to be true, but may not be. Okay. So let me just reproduce that formula or that mapping down here, just so I have it in front of me. Okay, so I have this mapping, which I call tau x naught, from the tangent space at x naught into, um, and an important part of this is that there exists a neighborhood O of x naught. Okay, and I can define this mapping like so. And so derivations from X naught for the CR mappings defined on O. Okay, and tau X naught is linear injective. Okay, all right, so some questions and some answers. Okay, so tau X naught is not generally surjective. Okay. Um, so that can be um, it can be made to be it can be shown to be surjective for I forget certainly for manifolds that are modeled on Hilbert spaces, and I forget whether it's true for manifolds modeled on an arbitrary Banach space. Uh, but it's certainly not true for general locally convex spaces. But I forget what the status is for Banach manifolds. Okay. um, my guess is for Banach manifolds, it's not generally true, but I don't know for sure. Okay. All right, so that's one part of this. Um, so then the other part of this is can you replace O in this statement with M? Okay, so certainly we can define, and we did define, a mapping from the tangent space into the set of derivations for M, and that was just the mapping that's in this mapping is well defined. Um, okay, as a mapping into here with M. Okay, so this mapping that we defined, there's nothing really to do with O in terms of the definition of that mapping. You can define that mapping, but then the question is the corresponding mapping still injective? Okay, okay, so let me say it this way. So we can define. And let me write it maybe as tau x naught bar to suggest that it's extended somehow from t x naught m into the set of derivations on CRF m, okay, not just an open neighborhood of x naught, and the mapping is defined in exactly the same way. Okay, like that. Okay, so there's nothing wrong with the definition of that thing. Okay, but we it's no longer known whether this thing is injective. Okay, so we know it's not surjective from the previous statement. Okay, and it's not generally known whether it's surjective. Certainly, our proof of surjectivity from last time um, uh, uh, is invalid to prove the injectivity of this thing if you replace O with M. Because how did we prove this last time? Well, we used the Hahn-Banach theorem. So we chose O to be the domain of a chart. Okay. And then in the chart, we found a function. Okay, remember that a derivation maps functions into scalars. So we found a function which uh, um, which when you apply this mapping for two different tangent vectors to that same function, that they're different. Okay, and we did that by defining the function to essentially be a linear function using the Hahn-Banach theorem. Okay, so that construction only is going to work on a chart domain. There's no such thing as a linear function on a manifold. Um, but if you could extend that linear function that I defined on O from last time, if you could extend that function to all of M, okay, so it's defined on O like I had last time, and then you can extend it to be defined globally, then that construction that I had last time will work, and it will prove injectivity of that mapping for all of M, okay? But, okay, that extension may not be possible, okay? So this, oops, this has to do with the possible lack of extension of functions in defined on the neighborhood O, so CRF O to functions in CRF M. Okay, and again, if you're familiar a little bit with differential geometry, you know that this has to do with what are called partitions of unity, or possibly some other similar kind of a construction. Okay, so I'm not talking about partitions of unity. Okay, and again, if you know what they are, good. If you don't, then okay. Okay, partitions of unity essentially are just used to make extensions of this kind. So you can take local constructions and extend them to global constructions. Okay, so where do the problems arise here? If M is finite dimensional, okay, all right. Let me maybe do it this way. So 3, I guess I didn't have to erase that. If M is finite dimensional, then life is good. Okay, then the mapping tau x naught. Okay, and so let me so tau bar x naught is a bijection. Okay, so in other words, there's a one-to-one correspondence between tangent vectors and derivations at x naught. Okay, in the finite dimensional case, and so as when I talked about tensor products, I do mean to imply here that if M is not finite dimensional, okay, so possibly even modeled on a Banach or Hilbert space, sorry, Banach space, um, then then this mapping may not may not be a bijection. Okay, and so in fact. If and I should have said this, but I just forgot. So if M is modeled on Hilbert space, so in particular the finite dimensional case, this is true. And the reason is, again, it just has to do with partitions of unity. Hilbert spaces possess partitions of unity. And that has to do with the fact that their norms are nice. Okay, so the problem of doing this for general Banach spaces has to do with the nature of the norm. Some norms are not very pleasant. Okay. All right. So there's some things that you kind of have to be careful of. Now, this lack of bijectivity of this mapping, it's kind of interesting and important. Okay. Um, and so in particular, when it does hold, okay, so this is this particular construction here is an instance of a more general kind of philosophy about differential geometry, where you replace a geometric object, in this case the tangent space, with an object that acts on functions, in this case a derivation. Okay. And that's a powerful idea when it applies. Okay, and what I'm saying here is that it applies in the finite dimensional case, or some extensions of that, but it does not generally apply in infinite dimensions, even for norm spaces. Okay. Um, so this is one of the places where infinite dimensional geometry uh, is different from finite dimensional geometry. And so, all of this stuff is about where infinite dimensional geometry is different from finite dimensional geometry. Okay. Okay, so that's all I wanted to say about things that don't work, and that's not by any means saying that that's all that doesn't work. There's lots of stuff that doesn't work, but those are some things that we can talk about now from what we already know. Okay, good. So now, let's talk about the structure of, well, we've talked about the structure of tangent spaces. Now let's talk about this thing called the tangent bundle, and talk about its what kind of structure it possesses. Okay, so let's talk about the tangent bundle. Okay, so we know what the tangent space is. Well, we know what a tangent vector is, and it's an equivalence class of curves. So the set of all tangent vectors at a point is called the tangent space of that point. And so when we define the tangent bundle, we merely take the bundle of all of the tangent spaces. Okay. Um, okay, so let's let M be a CR manifold. And sorry. Okay, the tangent bundle of M is TM. Sorry. Okay, so this is the disjoint union of all the tangent spaces. You don't know what the disjoint union is, it kind of doesn't matter in this case because all the tangent spaces are disjoint anyway. There's no way for a tangent vector at one point to also be a tangent vector at another point, so you can just think of this as being the union, no problem. Okay, so that's what the tangent bundle is. Now, what we're going to do is, so we now show that Tm is a vector bundle over M. Okay. So first of all, we'll show that it's a manifold. Okay, and we do this by producing an atlas. Okay, so and the atlas that we're going to produce has as its starting point charts for M. Okay, so let's take a chart for M. U phi, phi, V phi. Okay, and define um, T U phi, T phi, T V phi. Okay, so I just T everything notationally. I need to tell you what those are. Okay, so TU phi is the set of all tangent spaces at points in U phi. So it's the subset of TM where this union is taken not over M, but over just U phi. Okay, so like that. Okay. V phi, V phi is simply V phi cross V phi. So the T's that I'm introducing here, those are just notation. Okay, so and I'm saying precisely here what those things are. Okay, but don't attach any meaning, independent meaning to those at this point. They're just notation. We'll see, in fact, that these things have a specific meaning, but for now we don't know what they are. All we know is what I'm telling you. Okay. All right. So TV phi, or sorry, T phi. Okay, so it's going to map T U phi into T V phi. All right, so what's it going to do? It's going to take a tangent vector, oops, tangent vector at some point x in U phi, because that's what this is. It's a set of all such tangent vectors. So an element in TU phi, by definition, is going to be an equivalence class of curves at some point x in U phi. All right, and it's going to map it to, by definition, phi of x, and then phi composed with gamma prime at 0. Okay, so that's my, so I take a chart for M and I do this construction, and what we're going to see is that this is a chart for TM, and then if you take an atlas for M, and you do this to each of the charts in the atlas, then you get an atlas for TM. Okay, and that's a proposition. All right, so with the above notation, okay, so first T U phi, T phi, T V phi is a chart for EM, and if A is an atlas for M, then TA, which is simply the set of all T U phi, T phi, T V phi, where U phi, phi, V phi runs over all charts from the atlas for M. Okay, so this is an atlas for M, sorry, TM. Okay, and so up here I started with a manifold that's of class CR, and the manifold TM uh, is of class CR minus 1. So giving PMACR minus 1 differentiable structure. Okay, so first let's show that it's a chart. So remember what it means to be a chart. Um, it just means some very simple things. So it means that it should just be a bijection, that T phi should be a bijection from this one onto an open subset of this one. Okay, that's all we need to show that it's a chart. Okay, so first we claim that T phi of T U phi is equal to phi of U phi cross V phi. Okay. All right, so we essentially did this um, last time, but let me just remind you of how that went. Okay, so clearly, by its definition, right? So the definition of T phi here, okay, it's clear that so this thing is in phi of U phi, and this thing is in V phi. So it's clear that the image of this is contained in the thing that I'm claiming it's equal to. Okay, so clearly image of T phi is a subset of phi of U phi cross V phi. Okay, so I need to show that every point in here is in the image of T phi. Okay, so let's let X and V be in phi of U phi cross V phi, and I need to construct a point in T U phi, okay, so a tangent vector at some point, whose image under T phi is equal to this thing, okay? All right, take, um, let's call it maybe X bar to be the inverse of X, obviously. Okay, so that's going to be my point in M. Okay, and as we saw last class, okay, there exists a curve, gamma V. Okay, so this is a curve defined on some interval. So let me just say it this way. There exists, sorry. There exists a curve gamma V at X bar such that um, uh, such that so okay right such that phi composed with gamma v prime at 0 is equal to v. Okay, that's what we showed last time. And that it's easy to do this. You take gamma to be the inverse of x plus tv. Yes, okay. Okay, good. and that does it, right? Because then by the definition of T phi, right? So remember that T phi is defined like this. Um, then T phi of um, gamma v at x bar is equal to x v, right? So that shows that every point in here is in the image of T phi. Okay, good. Um, moreover, okay, by the fact that tangent vectors are equivalence classes of curves, okay, so if you look back at our definition of equivalence, right? So the definition of equivalence is the two curves are equivalent. Two curves gamma 1 and gamma 2 are equivalent if that's true, okay? Um, and this actually immediately gives you injectivity of the mapping T phi, because if the image of 2 points is the same, and the images exactly look like this, then that means that the curves gamma 1 and gamma 2 are equivalent and therefore define the same tangent vector. Okay? Okay, by the fact that tangent vectors are equivalence classes of curves. Okay, T phi is injective. And that shows that the thing we're looking at is a chart. And sorry, the only thing I haven't, forgot to mention, but it's clear, is this is an open subset of U phi cross U phi. So it's an open subset of V phi cross V phi. Okay. All right. So just to make sure we understand, it's an open subset because it's a product of open sets. That's the definition of the product topology. Okay. All right. Now we need to show the overlap condition. Okay, so in order to show that the collection of all of these charts, okay, as you run U phi phi V phi over an atlas for M, that these things will satisfy these charts for the tangent bundle satisfy the overlap condition. Okay. All right. So now let U phi phi V phi and U psi psi V psi be overlapping charts from A. Okay. Right, so I need to show that the overlap condition is satisfied for the two tangent bundle charts. Okay, so this is not hard, but let's just see how it follows from the definitions. Okay. All right, so what you need to consider then is the mapping T psi composed with T phi inverse. Okay, so that's the overlap map for the tangent bundle charts. Okay, so this is going to be applied to a vector x v. Okay, Okay, and so xv is in phi of u phi cross v phi. Okay, and then I'm going to map that into a point in psi of u psi cross v psi. All right. Okay, so again, we basically just apply the definitions. All right, so what's this? So this is going to be a tangent vector at phi inverse of x. Okay, um, by the definition of T phi, right? So it's gonna certainly be a tangent vector at some point, and that point, of course, is going to be T phi phi inverse of x, um, and the curve is going to be any curve which for which phi composed with gamma prime at 0 is equal to v. Okay, so let me call such a curve. Just let me call that as I've done, right, as I've done up here, right? So I need a curve gamma that satisfies this formula here. Okay, so let me just call that curve gamma phi. All right, so the point is that this is T psi of this thing. So it's gamma v at phi inverse of x. Right, so that's a tangent vector at phi inverse of x for a suitable gamma v. All right. Now I apply the definition of sorry, the definition of T phi. Okay, so the definition, sorry, T psi, and that's psi composed with phi inverse of x. Okay, so I apply psi to the point at which the tangent vector resides. And then I go, sorry, psi composed with gamma v prime at 0. Okay, alrighty. So this is what it is. And then I do something which is by now sort of familiar. I insert a phi in there like that. And, this is true as long as, this is valid as long as x is also in u psi. Okay. All right, so now I'm going to use the chain rule to differentiate that thing. All right, and I'm going to use the chain rule on this composed with that. Okay, so this is psi composed with the inverse of x, and then it's d psi composed with phi inverse at, okay. So what's the point at which this thing is evaluated? Well, it's evaluated at um, right, yes, at x, right, okay. Okay, so it's evaluated at let me just make sure I have that right. Yes, that's right. That's right. Okay. Okay, good. All right. So it's like this, acting on phi composed with gamma v prime at 0. Like that. Okay, so that's just applying the chain rule. Okay, in other words, and then you use the fact, of course, that phi composed with gamma prime is v. Right, so it's psi composed with the inverse x d psi composed with phi inverse of x v. Okay, good. All right, so this thing So what do I need to be true? I need for this thing to be, according to my claim, the differentiable structure for Tm is going to be of class CR minus 1 if M is of class CR. And so why is it CR minus 1? Well, it's CR minus 1 because what's this thing? Sorry. Uh, this thing, I'm sorry for getting a bracket there. All right. Um, so this guy, because U phi V phi U psi V psi are compatible charts for M, I know that this one is of class CR. Okay. And therefore its derivative here is of class CR minus 1. Okay, so that's why the overlap map is of class CR minus 1. Okay, so this mapping is of class CR. Okay, so why is it? Let's make sure we understand exactly why it is like this. So first of all, this is a mapping into a product. Okay, so we know that a mapping into a product is of class CR minus 1 if all of its components are of class CR minus 1. Okay, so this is of CR, so certainly this is of class CR minus 1 because R is greater than R minus 1. And because psi composed with phi inverse is of class CR, this one, okay, that's by definition of what it means to be of class CR. I think I just said that this is of class CR minus 1. It's of class CR, and therefore this one, by definition of what it means to be of class CR, is of class CR minus 1. So both of the components of this product are of class CR minus 1. Okay, in any case, the overlap map is of class CR minus 1. Okay, so that's the manifold structure for the tangent bundle. Okay, so these charts T U phi T phi T V phi are called natural charts for TM. Okay. And so the point is that if you have an atlas for M, then the collection of natural charts for TM associated with that atlas are an atlas for TM. Okay, and that's, I guess you'd call that the natural atlas. And so then that atlas, therefore, defines for you a differentiable structure. Okay. And then remember, once you have a differentiable structure for a set, that turns it into a manifold, and then once you have that differentiable structure, then there's maybe all kinds of other charts which are compatible with the charts defining the differentiable structure. Um, and so my point is, not all charts for sorry, for TM are natural charts. You're welcome to use any other kind of chart that you want. But the manifold structure that we just defined was defined using natural charts. Okay. All right. Okay. Good. Now, we actually proved more than that this is a manifold structure. We also proved, okay, let's take a look at this overlap map here for these natural charts. Okay, so this overlap map has the form of, okay, so let me say the corollary and then I'll actually write down what I want to say here. Okay, so this is a vector bundle. Uh, and it's base space. is M, and the fibers have the vector space structure inherited from the set of derivations. The vector space structure, sorry, let me of Tx naught M is inherited from the set of the vector space structure on the set of derivations. Okay. By the map that we dealt with previously, this tau x naught map. Okay. Proof. Okay, so so the overlap map. So let me just sort of be a little bit terse with this proof. So the overlap map okay, so T psi composed with T phi inverse, okay, that we just wrote down. Right? Is, in fact, a local vector bundle isomorphism. So, in fact, it's a CR minus 1 from okay, so phi of the intersection cross b phi to psi of the intersection cross b psi. Okay, so that's clear. Okay, so all right, so this guy is a diffeomorphism from this one to this one. Okay, and then on the fibers, these, okay, this mapping is an isomorphism. Okay, all right, because this mapping d psi composed with phi inverse is certainly linear, and it has an inverse, which is namely d of phi composed with psi inverse. Okay, so it's linear and it's invertible with a continuous inverse. Okay. All right, and so that's all you need to show that this thing has a vector bundle structure, because what it shows is that in the previous proof we actually constructed not just an atlas, but a vector bundle atlas. Right, so that gives it the vector bundle structure. Okay, and the vector. Yeah, let me do the fibers first. All right, so the vector space structure fibers agrees with the vector space structure on V phi. Okay, so if I have a chart, phi, U phi, phi, V phi. Okay, so there's two vector space structures that I'm talking about here. Okay, uh, coming from both the local vector bundle chart on the one hand, and on the other hand, the injection of T x naught m. So sorry. Okay, so I have the way when I proved this this linear injection property of the mapping tau x naught, what I did was I showed first that this thing, these sets are in bijective correspondence. Okay, and then I had an injection into the set of derivations. Oh, okay. And what I actually showed in the proof was that this map was linear. Okay. And therefore, because this map is in bijective correspondence with this one, and the bijective correspondence between that I used between these two sets is exactly the same vector space exactly the same correspondence as comes from the local vector model charts. This shows that the vector space structure on here uh, is the same as the vector space structure on here, inherited by that linear map. Right, so it's a complicated way of saying what in fact is something very simple. And so, period. Okay. All right. So, I'm sort of writing mnemonics here, as I sometimes do in these arguments that would take a lot of words and a lot of symbols to prove precisely, but are clear from things that I've already done. All right, so that's the vector space structure. And then the final thing to prove is that the base space, the base space is M. Okay, so the points in TM that are mapped to all right, so remember what the base space is. So the base space of a vector bundle, the definition is that it's the set of points in E, which in any vector bundle chart are mapped to 0 in the fiber part. Okay, so points in TM that are mapped to points x0 by charts T phi, oh sorry, T U phi, T phi, T V phi are exactly points for which. Okay, so again, let me give this thing a name. Okay, so what's a point in TM? So a point in TM is an equivalence class of curves. Okay, so these are points, let's say gamma at phi inverse of x. Okay, so if in the chart they map to x, then upstairs in the manifold, that's a tangent vector at phi inverse of x, for which phi composed with gamma prime at 0 is equal to 0. Okay, so these points correspond to the equivalence classes of trivial curves. In other words, they're curves that just sit there. Okay, so t goes to x. Okay, so constant curves. Okay. All right, so that shows that um, uh, um, the the trivial curve at x, okay, maps to a point of this form in the vector bundle chart, and so therefore corresponds to points in the base space of M. Okay, so that gives the correspondence of M with points in the base space. Okay, so that finishes the corollary. Right. Okay. So let's maybe look at some um, examples of tangent bundles. Okay, so always, well, not always, I guess, but often, um, um, the simplest place to start thinking about geometric concepts is to work with open subsets of locally convex spaces. Okay, so let's let V be an LCS and let O be open. Okay, so as we've seen, that's a manifold. Right? So what's TO? So we're gonna show right, sneeze that as a vector bundle, it's isomorphic to the trivial bundle O cross V. And I will write down the explicitly what the vector bundle isomorphism is, and then you can verify that this thing is in fact a vector bundle isomorphism. Okay, so indeed, if X in V is in O cross V, so this is a construction that we've seen before. Just in this case, it's particularly simple because we don't have to deal with charts. So we define gamma X in TO by um, by the equivalence class of the curve T goes to X plus TV. Okay. All right, so you have to prove then that this thing is a vector bundle isomorphism, so you should show that it's well defined. Um, uh, so in other words, it's this representation is independent of um, of equivalence class, and you should show that it's of class CR, and you should show that it's an isomorphism of vector bundles. None of those things is hard. Okay. Okay. All right. So notice that if uh, so now so I said that when we had this chart, U phi phi V phi, okay, then we had this symbol TU phi, T phi, TV phi, okay, and those T's were just sort of symbols, but now they have at least two of those T's have precise meaning. Just remember the definition of this was set of all tangent spaces. Okay, and T V phi equals sorry, V phi cross V phi agree with um, uh, T being tangent bundle. Okay, so the sort of just symbolic meaning to these T's that I was using when I wrote down the definitions of these things, this literally means tangent bundle now in both of these cases, since we know the meaning of the words tangent bundle. So then you wonder what T phi means. Well, we'll get to that. Okay. All right. uh, are all, gosh, sorry, tangent bundles trivial. Okay, so that is if M is a CR manifold, is there? And so for my statement to kind of make sense, I'll say that this is connected. Is there an LCS V and a CR minus one vector bundle isomorphism from T M into M cross V. Okay, so that's my question. Then that's what I mean when I say are tangent bundles trivial. So I mean, is it isomorphic as a vector bundle to a trivial vector bundle? Okay, so I can see here that this is true uh, when O is an open subset of a locally convex space, right? So this statement here was exactly that this thing's isomorphic to a trivial bundle. Excuse me. And so here the answer is no, and it's no in trivial. It's not one of these things that is anything to do with infinite dimensional things. So um, uh, fact is that the tangent bundle of the even dimensional spheres are not trivial. And so maybe even let me make a stronger statement than that. TSN is trivial if and only if n is odd. Okay, so just the n-dimensional sphere. So, for example, the two-dimensional sphere is not trivial. Okay, and I shouldn't really say trivial. I should really say um, trivializable. Okay, so trivializable would mean that there's a vector bundle isomorphism like this. So, essentially it's trivial, but this isomorphism may not be naturally defined. Okay. All right, and so for n equals 2, uh, this is what's known as the Hairy-Ball theorem. Okay. And so let me try to tell you some intuition behind the Hairy-Ball theorem. Definitely not a proof of the Hairy-Ball theorem. Okay, so if T S2 were isomorphic to S2 cross R2, and it would have to be R2 because S2 is two-dimensional, and the fibers of the tangent bundle have the same dimension, or more generally, they're modeled on the same locally convex spaces as Rm. So this thing has to be some two-dimensional manifold. So let's may as well make it R2. Okay, so what would this mean? Um, Okay, so this says that every tangent vector can be written as um, a pair of things. Okay, okay, so let's write these maybe as E1 of x, E2 of x. Okay, so corresponding to the basis vectors um, in R2. Okay, so there's two linearly independent vectors, and E1 and E2 depend smoothly on X. Okay, so in particular, okay, if you take any one of these two assignments to every point, so these are going to be vectors in R2, right? So these are basis vectors in R2. So these are, to be clear, this is in um, 2 cross R2, right? So each of these is a two-dimensional vector, corresponding, again, these are the basis vectors for R2. Okay, so in particular, there exists a continuous nowhere vanishing vector field. We haven't talked about vector fields, but I know that you've seen the notion of a vector field in vector calculus, and you think of a vector field as just assigning a tangent vector to every point. We'll hopefully talk a little bit about vector fields. Okay, there exists a vector field. And so, you could take either one of E1 or E2, for example, on S2. Okay. All right. So that's one of the implications of of S2 being trivial, is that there is a continuous, nowhere vanishing vector field on it. All right. Um, And so the way you kind of think about this and why this is called the Hairy Ball theorem is you can think of the two-dimensional sphere as being like so, right? And so this is saying that at every point you can assign a non-zero tangent vector, right? So a vector in, if you stick S2 inside R3, um, these things will be tangent to the sphere. Okay, like so. All right. But what the Hairy Ball theorem says is that if you have any such a continuous vector field on S2, and so again, a continuous vector field just assigns a tangent vector to every point, then it must vanish somewhere. Okay, so it must be the case that, and so these are you can think of this as being like hairs on the S2 as being a head of something, and the tangent vectors as being strands of hair. And a continuous vector field means you arrange the strands of hair in a certain way, so that's a hairdo. And so the Hairy Ball theorem says that you can't lie your hairs flat. There has to be a point at which you're going to have a hair that sticks out. That's the intuition behind the Hairy Ball theorem. Okay. But and so there's various ways of proving the Hairy Ball theorem. Most of the standard ones involve algebraic topology. Um, but there's a nice paper by John Milner in the American Mathematical Monthly where he proves the Hairy Ball theorem um, just using elementary. I think the most complicated thing that he uses is the fact that in Rn, any smooth function can be approximated by a polynomial function. Or sorry, any continuous function can be approximated by a polynomial function. And so he gives a proof using elementary analysis. Okay. So the point is that manifolds do not have trivial tangent bundles generally. Okay. All right, good. So that'll finish things up for today. Next time, what we'll do is we'll talk a little bit more about tangent bundles, and then I'm going to talk about what are called higher order tangent bundles. Okay, so that's where we'll pick up on Wednesday. Bye.